Okay, I'm Aaron, and this is my Unit 6 Progress Check FRQ 2. So in part A1, we're asked to draw the arrows to indicate the direction of the moon's velocity. So we know that it's moving in an elliptical orbit, so the velocity should be drawn at the tangent, like that, and like that. And then in part A2, we're asked to draw the direction of the moon's acceleration at points A and B. So we know that the due to Newton's laws of gravity, that it should be pointed towards the bigger mass, so like that. And that concludes part A. So at part B, we got to start with the conservation of angular momentum and drive an expression for the moon speed VB. So we could start with the angular momentum at A equals LB, and we could write I A omega B, or not omega B, omega A equals IB omega B. And we write this as R A M A V A equals R B M B B B. And since we know that the force at B isn't perpendicular, we need to get the sine portion of it. So we have to add sine to the end of this, sine theta. And now we're asked to solve for VB. So we actually cancel out the masses because it's the same. So we get RA VA over RB sine theta equals VB. And in here we're given that RB equals 5 over 2 RA, and there's a 53-degree angle. So I'm gonna get RA VA over RA 5 over 2 sine 53, and cancel out the RAs. And we get VA equals, and this 5 over 2 times sine 53 equates to about 2. So we get VA over 2 equals VB. And in part C, we're asked to sketch a graph of the moon's kinetic energy as a function of its distance. So we're told that at Ka, the kinetic energy is 1/2 mVA squared. So at Ra, we can put this here. And since we know that our thing is in orbit, that it will keep moving, so at RC here, it actually never reaches 0, but it gets close to it, so it'll be here. Since we know that it's squared, it'll have like a parabola type of shape. And that's part C. And in part D, we're asked to indicate whether the graph feature is consistent with the velocity and acceleration you indicated for part B, part A. So it is consistent, right? So we could go back to this part, and since we know that our acceleration is pointing like that, right? It's not perpendicular. We could actually break it up into two different components. One going this way, one going down. Well, this is the important part. And we know that the velocity is going this way, right? So at point B, we know that the acceleration is actually counteracting against the velocity that's going this way, so it's slowing it down, and that is consistent with our graph here. And we can see that it's getting less and less. And that's my FRQ. Thank you.